Hello, this is Mrs. Nearing, and this video is going to go over problems 1 and 2 from Kinetics Practice Set 3. So if you look at problem number 1, we're given a reaction mechanism, and a mechanism is basically the steps by which a reaction proceeds in real life. So a lot of times we are given like the reactants and the products, but it's not actually a one-step process. It might be a 2-step or 3-step or 4 or 5-step process. So it looks like right here we have a reaction that occurs in 2 steps, and we're told that the first step is the fast step and the second step is the slow step. And by the way, the slow step is also sometimes called the rate determining step, and we'll see why that is later. So rate determining step. So first thing we want to do is write the balance equation for the overall reaction. So we're basically adding up these 2 reactions to get an overall reaction. It's kind of like what we do when we add up 2 half reactions in a redox problem to get the overall balanced equation. And if you're wondering how to deal with this weird looking double arrow, you can treat it just like a regular arrow right there. So I'm going to add up everything on the left. So that's A, and there's 2 C's, and there's an AC2 molecule, and then there's another A. And then on the left, there's another AC2 molecule, and then there's 2 AC molecules. So you want to look for things that cancel out or that you can simplify. So AC2 shows up on both sides, so I'm going to cancel that out. And I'm going to notice too that there are 2 A's, so I'm going to rewrite that as 2A, and then 2C makes 2AC. So this is a balanced reaction, and since they're all 2's, no coefficients are all 2's, you can actually simplify it further into A plus C makes AC. Okay, so this would be my balanced overall reaction. Intermediates in this reaction, those are the things that are made in an early step and then used up in a later step, and they are neither reactants nor products in the overall reaction. So the thing that fits this definition in this scenario is AC2. It is an intermediate. So it's not a reactant, not a product. It's something that gets made early on, then used up right away. The rate law based on the mechanism, the rule here to keep in mind is the exponent in the rate law is going to match the coefficient in the slow step. The slow step, which is our rate determining step. So our rate law is going to match our slow step of the reaction, not necessarily the overall reaction. So I'm going to look at the slow step of this reaction, and in my slow step I have 1 molecule of AC2 and 1 molecule of A. So I'm going to say my rate is going to be K times AC2 times A, and that's my rate law. But I might say, wait, we just said AC2 is an intermediate. AC2 is an intermediate, and the rate law needs to be written in terms of the reactants, which are A and C. So if you have an intermediate in your slow step, this is what you want to do. And this is an excerpt from the textbook down here. This is, I think, page 626 if you want to look it up. But if the slow step contains an intermediate, then what you want to do is express the concentration of the intermediate in terms of the reactants of the overall equation, which might be kind of a confusing sentence. So let's take a look at what that would mean in practice here. So if you go back to our mechanism here, AC2 is my intermediate, and I want to express AC2 in terms of the reactants, which are A and C. So what I'm going to do is I'm going to look back at this first step, and it tells me it's fast equilibrium, and we'll talk more in Unit 6 about what that really means. But for right now, the thing to know is that that means that the rate of the forward reaction is equal to the rate of the reverse reaction. Therefore, because of the way that we write out rate laws, we can say that the concentration of A times the concentration of C squared is equal to the concentration of AC2. So basically, you look back at AC2, and whenever you see AC2, you plug in 1A and 2 C's. So it's kind of like the slow step. Instead of being AC2 and A, is A plus 2C plus A. That makes sense. So you're just substituting in whatever things were used to make your intermediate. in which case it's 1A and 2Cs. And these things are reactants, so it's perfectly fine to have those there. So what we're going to do is wherever we see AC2, we're going to substitute in 1A and 2 C's, which we could write as C squared. So that means overall, my rate law is K times A squared, because now I've got 2 A's, and C squared. So this is my rate law. Okay? And looking at problem D, what would happen to the rate if all the reactants were doubled? Well, both concentrations are being squared. So if I look at my rate law from up here, if I were to double A, then that would get squared, and then double C, that would be squared. So that would be 4 times 4. So my rate would increase by 16 times. Okay. Now let's take a look at problem number 2. Problem number 2, you're trying to figure out a rate law based on experimental data. Let's number these data sets. 1, 2, 3, 4. So let's first compare experiments 2 versus 3. If you compare 2 versus 3, notice X is staying the same, but Y is doubling. So it is going from, 0.4 to 0.2, so that's doubling. And if you look at what happens to the rate goes from 2.8 to 1.4. So the rate also doubles. So if you think about what scenario does this fit? So I'm trying to figure out what the exponent of y is. Is it a 0? Is it a 1? Or is it a 2? Those are my only options. Well, if it were 0th order and I doubled y, my rate would stay the same. If it were first order and I doubled y, my rate would double. If it were second order and I doubled y, my rate would quadruple. So if you ask yourself what fits, well, it looks like this fits. So it looks like y is first order. Okay, so I'm going to start writing that at the top. So rate equals k times y to the first order. We still don't know x yet. We have to figure that out. Okay, I'm going to erase this and make some room. If we're trying to figure out x, that's a little bit more annoying because there are no two reactions in which the concentration of y stays the same. In reality, if we were doing it, we'd probably set this reaction up a little bit different, but this is the data set we are given. So what can we do? Well, let's compare experiments 1 versus 2. So if we look at experiments 1 versus 2, you'll notice that x doubles and y doubles. Hey, buddy. Look at me. Nice. You're looking good. Give me a minute, okay? Like my hairstyle? It looks good. So x doubles and y doubles. And what happens to the rate here when x doubles and y doubles? If you look at the rates, 1.4 times 10 to the negative 3, 7 times 10 to the negative 4th, the rate also doubles. Okay, so x doubles, y doubles, the rate doubles. You're trying to figure out what scenario best fits this data. Well, our options are my rate could either equal y1 times x to 0, it could equal y first order x first order, or y first order x second order. So you ask yourself, which scenario does it match? Okay, well, if it was the first option, then if the y and x were both doubled, you'd end up with 2 times 1, you'd expect the rate to double. If we're the second scenario and they're both first order, you'd expect the rate to quadruple. And this last scenario, if one was second order, you expect the rate to go up by 8. And what do we see actually happen to the rate? Well, it goes up by 2. So that tells me that this must be the correct scenario. Okay, so that means we can go back up here to our rate law and say, okay, we now know that x is first order as well. Whoops, sorry, not first order. A little distracted here. X is 0th order. So we know that y is first order, but x must be 0th order in order for this data set to work. So this right here is our rate law up here at the top. We can also rewrite it in a simplified version. I'm kind of running out of room, so I'm going to write it down here. That rate equals k times the concentration of y, and this is our rate law. Okay, so calculate the specific rate constant. That means find the value of k. So to do this, we just choose a data set. Let's choose data set 1, and we just plug in numbers. So rate is 7 times 10 to the negative 4th molarity per second. Okay, k, and then y is 0.10 molarity. So I'm going to solve for k. I'm going to divide both sides by 0.10 molarity. And then when I do that, when I solve for k, it's important to pay attention to the value of k as well as the units of k. So value-wise, when I divide these, I get that k is equal to 7 times 10 to the negative 3rd. Whoops, I should have kept my sig fig here. In terms of units, I've got molarity divided by molarity. So the molarities cancel out, and my units are 1 over seconds, which is the same thing as seconds to the negative 1. Okay, so this is my value of k. So pay attention to units when you're calculating k. And then I want to figure out which of these reaction mechanisms is consistent with the observed data, basically consistent with the rate law I already determined. So let's work through our scenarios. If this first reaction were the correct mechanism, then my rate law would be determined by the molecules in the slow step. So my rate law would be x times y. Because I have one molecule of x and one molecule of y in my slow step. The second scenario, the molecules in my slow step are y and m. But remember, m is a intermediate, so m can't be included in the rate law. So what I do is wherever I see m, I'm going to go back and substitute in 2 x's. So if an intermediate's part of the slow step, then you look back at the previous fast equilibrium step, and you're going to substitute in whatever reactants in that step for your concentration of your intermediate. So in this case, my rate law would be k x squared times y. And this last scenario, my slow step's the first step, and my slow step just involves one molecule of y. So my rate would be equal to k times y. So which of these 3 mechanisms matches my determined rate law up here? Well, my determined rate law is rate equals ky, so it looks like mechanism 3 matches it. All right, and that's problems 1 and 2 for you. More to come.